Hello, good morning. It's a pleasure to be with you. I thought of what should I talk about when I have this incredible opportunity to stand in front of a crowd like this. And I realized that maybe the thing I should talk about is what powers us all. How about talking about sunlight as we know it? And the reason why I thought this would be a good place to start is because it turns out there are some amazing transformations that are about to come upon us, both in a form of global warming and in a form of trying to figure out how to stop it. And as a way of maybe coming with a solution, one thing you can imagine doing is say, well, what if I can power the world with things that has been powered all along, which is sunshine? What if we can take some of the sunlight and run the electricity that spends about half of the energy that we utilize to run the world as we know it? What would that do? Oh, by the way, if we ran our cars on electricity, it would be another amazing thing to do. But let me ask today, how much of today's electricity is actually used from the solar generation? And it's about 1%. Well, it doesn't sound like very much. And it doesn't unless you put it in perspective. And perspective is very simply this. Solar deployment, as we know it, has been growing about 40% annually, year after year after year. Last 15 years, go ask and check the data, and every single one of the data points will actually exceed any prediction we have ever made. If you had asked us a few years back, when will we have 200 gigawatt peak installed solar technology, the answer would have been, oh, I don't know, in about 15 years from now. Well, no, actually it's today. And if you project, well, compound interest tells you that by year 2030, 155% of world's electricity will be provided by solar, which is a bit of a extrapolation, a bit too far, but it is on the growth. And then the question becomes, well, what's next, and how do we actually embrace it? Because it is transformational, and it is really disruptive, and it is actually quite a challenge to absorb inside the system as we know it. So let me tell you about the dominant solar technology, and you might have seen it driving around towns here, that roofs of Massachusetts homes do have indeed a lot of solar installed, and typically in the form of what we call residential installations. Now, the other way you might find solar is if you drive around the fields next to, let's say, roadways these days, you can find these large installations of what are called utility installed solar. These are incredible installations from perspective of providing us that solar energy. The question then becomes, all right, well, how are we doing? From ability to actually replace coal and gas-burning power plants with solar installations, we better meet the cost targets. Boy, are we doing our job? Are we doing our job as scientists, technologists, people who really want to come up and make a difference with what we are working in labs with? And the answer is yes. By the way, the thing to note is that there are two parts of solar you have to worry about. There is a module, and that's the thing you see on top of a home. And then there is what we call a balance of systems. All the wires you don't see, and yet are fairly important for the final installation. Someone needs to mount that cell on your roof. You need a little bit of aluminum to frame it and hold it on the roof. There better be wires and something that connects it to the grid. All these things do cost extra money. How much extra? Well, that's what this plot shows. The cost of the module, the actual cell that absorbs light, we worked so hard on it that since 2008, the cost went down about 85%, an incredible drop. But balance of systems, we really haven't had a chance to work much on it. Or maybe it's that we cannot really do much better than what we already are doing. Is that maybe the real challenge? Well, how do we figure this one out? How come balance of system costs quite as much as it does? Well, I would argue that the reason is because solar cells weigh as much as they do. And you say, well, that's kind of ridiculous. I mean, why would the weight matter for a solar cell? Well, it does. If I want to deploy it, I better come up with something that's easy to either unroll or screw down to the roof, or indeed, other installation. If I can change the weight of the cell, maybe I can change the paradigm of what solar really, really means. And how would I use it as I think about installing it? All right, let me show you some options, new options that we've been kind of tossing around the lab for a decade or so, thinking about what else beyond silicon that's on the left of that graph. Typically make silicon wafers and then make solar cells out of it. And this is a very simple material that generates a complex manufacturing process to give you the cell. Can I switch that around? There are many so-called nanomaterials that we invented over the past decade or two, so-called molecules, quantum dots, polymers, variety of these little things that can give us solar cells as well, except we would never think of them as really useful materials because they're very complex to make in a beaker. And then the next step is simply spraying them on, printing them with printers like this. Well, how old is this printer? Oh, it has been finally developed last year. And here it is, printing 100 molecules, thick layers, in order to make a thin layer that might be used as a light-emitting device or a solar cell, indeed. Indeed, this printer might revolutionize the way we think about what it means to print a solar cell. Oh, but wait. I'm still printing on a piece of glass. That's not going to solve my weight issue, although it might give me a unique way of using different material sets. Indeed, by printing, I can go from a wafer, and this is just a close-up view, the wafer thickness compared to the hair thickness, compared to the present commercial thin films, compared to the new thin films that we imagine we should be able to do. And I'll show you some of these. Because the key next advancements are ability to make lightweight and integrated solar that will be on any surface you touch without you even knowing it's there. How would that look? Well, let me show you one. This is a piece of paper, and my solar cell is made of organic dyes. And you say, well, what's that? Well, actually, there are pigments used to color blue and red cars. Those can be used as semiconductors, just like silicon can. And here it is, one of those solar cells. I'm going to go ahead and attach it to some electrodes, shine some light on that piece of paper that has been painted, and you can run a little electronic device with it. You can now imagine having power on any surface you touch. As a matter of fact, what would it be like if I actually use this as a true piece of paper? Let me feed it through a laser printer and see what happens. I mean, I would, in a lab, officially call this a stress test in order to justify my research, right? But at the end of the day, I've just submitted this cell through a 300 Celsius thermal cycle, printed a label on top of it. Really, it shouldn't work anymore, but shine light and it still does. The way to think of solar now means that you can find it on any surface you can using new technology that could be roll-to-roll, abundant material sets that are widely available, lightweight and easy to deploy, so light, here is another one, it is so light that it can actually sit on top of a soap bubble because it weighs micrograms. You don't even know it's there. What would that imply? Well, it implies that any surface you touch, newspapers, any surface you touch, would be able to be solar active. And where would that matter? Well, it actually would matter a lot in places like this, places that have no access to grid electricity and hence rely on solar installations to power their villages. Well, how did this solar cell get to this village? Well, this way. And that person carrying the solar cell, he or she doesn't care what is the efficiency of the cell. The only thing they care about is how many watts am I carrying on my back per kilogram of the thing that I have on my back. Give me a very lightweight cell and I'll be able to outfit that village much more rapidly, deliver it much more rapidly into it with solar technologies. What are other goofy ways we might see solar deployed? Well, how about this one? This is a solar cell made of things called quantum dots, really small chunks of stone that could be optically active, absorb light, give you electricity back. And as a result, you might find it in formats like this, sunglasses. Now, why would you care about having sunglasses outfitted with a solar cell? Well, maybe you never want to recharge your hearing aids because you never would have to. Because indeed, there will be power right next to your ear. Maybe your wireless earphone would be a way to be powered using this particular technology. Indeed, maybe if you're in a warm climate, you want to have a little thermoelectric cooler behind your neck to cool you down. There are options, and look just how cool they are. I mean, that's the other thing to look at. Now, I'll show you a really cool one, though, because some of you might say, well, in a typical room, I don't want to wear my sunglasses, but you might want to wear these solar cells. Also made of molecules, unique molecules, molecules that do not absorb any visible light. Well, that's ridiculous. Solar cells better absorb light, you say. Well, I agree. Hence why we design solar cells that don't absorb any of the visible light, but do absorb ultraviolet and infrared light. So you can make a cell that looks as transparent as a piece of glass. Here it is. That's an actual solar cell. The way it works is that anytime UV or IR light, ultraviolet or infrared light, hits this particular cell, it converts it into electricity. Visible just goes through. And so you can make devices like this. This is a little e-reader, electronic reader that's been covered with one of these solar cells. And what we're doing is we're covering the e-reader with a notebook and then uncovering it. On the right side is the voltmeter that tells you how many volts you're generating. Anytime you uncover it, 10 volts come out. Anytime you cover it, the voltage goes down to 0 because no room light or sunlight is hitting your e-reader. But let me show you exactly what you have been looking through so you get a sense of how transparent this is. That's your solar cell. That's your solar cell that can be now deployed on any surface without you knowing that it's even there. That's a solar cell that can now indeed be integrated with your regular glasses, if that's what you want to do. This e-reader, you would never have to recharge it again, ever. Because in a matter of just a few days of room light, half an hour of sunlight, you'll be able to recharge its battery fully. And the battery typically lasts a couple of weeks. How would you relate to your electronics if you never had to recharge it again? How would you relate to your power if you never have to worry, will it be there or not? Because any surface you touch would have a micron-thick film that would indeed absorb the light and give you electricity back as you need it. Start with something small like this, because one thing I should warn you, everything I've shown you here today is new. And any hardware technology takes about a decade to go from a basic invention to impact where 1 million people can hold it in their hand. Is it as simple as a zipper or Velcro that took about 12 or 13 years, or more complex like organic LEDs that took about 20 years to go and commercialize from the basic idea to impact? As a result, take a little while, but one day, this will be the goal. Come up with a way to indeed outfit every surface we touch and every surface we look through to provide you ubiquitous access to power as we need it. Thank you.